Why isn't the autofocus working? Come on. Come on. Focus. Okay. Hello, class. I'm going to turn my camera off and then back on again because it's not autofocusing. Hope everyone's doing well. Just an FYI, my internet has been a little bit spotty lately, so the stream might be a little bit choppier than usual. Please let me know in the chat if it cuts out or you can't see what I'm writing or understand what I'm saying, and I will repeat it. Okay, let me try this again. Can you autofocus now? There we go. Nice. All right, so I'm going to go ahead and get started. So we have a pretty straightforward lesson today. All right. So there's something called rotational kinetic energy. So just like there is regular kinetic energy, so the regular kinetic energy we would call translational kinetic energy. So that's the kinetic energy you have when something is going from point A to point B. All right? But if we think about something that's spinning in place, it's moving, it's just moving in place, it's spinning. That's rotational kinetic energy. So that's the kinetic energy contained in a wheel, for example, or the kinetic energy in a propeller, or the kinetic energy in a tornado, or the kinetic energy in a saw blade as it's spinning. So even though these things might not be going from point A to point B as a whole, they might not be translating, they are carrying kinetic energy, okay? And you could harvest that energy, okay? So if we think about a wind turbine is taking the translational kinetic energy of the wind, because the wind is blowing from point A to point B, and turning it into the rotational kinetic energy of the wind turbine, which is then converted into electrical energy to power your home, okay? So the formula for translational kinetic energy is the exact same one that we've been using for this entire school year so far, which is 1/2 mv squared. All right. You know what I'm going to do? Get another piece of paper. I don't know if you guys notice what's happening here, but so it's kind of interesting. So notice how if I have my jacket on, which is a dark color, so if I put this over the screen, it tries to correct for the darkness of my jacket by making the screen brighter, which then washes out my writing. Okay? You see how it does that? Now if I remove my jacket Now it sees that most of this is white, so it darkens it down. So it's looking at, the camera is looking at what proportion of the screen is dark, and then it's correcting the brightness for that automatically when I would like it to just not correct the brightness. So while I'm writing, I'm making it correct the brightness, which makes my writing invisible. So I'm going to take this off. Then it's going to work fine. Actually, you know what? I'm kind of cold, so I'm just going to stick this arm out. Okay. And then I think it won't do that anymore. Let's try. Yeah. Okay. So you look at, watch. If I do this, it doesn't saturate it. But if I do this, it saturates it. See that? Okay, so translational kinetic energy is the form of kinetic energy that we've been using throughout this entire course. Okay? But there is also a rotational kinetic energy. And rotational kinetic energy is obtained from translational kinetic energy using the analogy between rotational motion and linear motion, okay? So if you recall, what is analogous to mass is inertia, okay? And what is analogous to linear speed is angular speed, which is represented by omega. So this is the formula for rotational kinetic energy. So basically, the faster something is spinning, the more rotational kinetic energy it has. Okay? So that's a new formula for today. All right, if something is spinning, it has rotational kinetic energy. So what if you have something that is moving from point A to point B and it's spinning while it's doing that? So you have something that's spinning, and as it's spinning, it's going from point A to point B. So then it has both translational and rotational kinetic energy. Okay? And so the total kinetic energy is going to be the sum of the translational and the rotational kinetic energies. So your total kinetic energy is going to be 1/2 mv squared plus 1/2 I omega squared. Okay, so that is your total kinetic energy. Now, under normal circumstances, something can be spinning. You know, you can make something spin and you can toss it, and the rate of spin, which is indicated by omega, and the rate of translation, which is indicated by velocity, those two things are completely unrelated. However, sometimes you get a situation where the thing is rolling. Okay? So let's talk about rolling. So when something is rolling, this means that translation and rotation are related. Okay? Because think about it. if you do one full rotation, okay, if you do one full rotation, then that means that the wheel moved forward by a certain amount. Okay, the rotations are related to how far you move. That's how the odometer in your car works. Okay, the odometer in your car doesn't use GPS to figure out how far you go. Okay, the way the odometer works is it's measuring how many times has the wheel spun. And then it's doing a calculation and it's saying, well, if the size of the wheel is this and it's spinning this many times, you can deduce how far it goes. Okay? And actually, this is kind of interesting. In old cars, if you put the car in reverse, it would actually, the odometer would go backwards. Nowadays, cars actually, they have corrected for that. So, you used to be able to just like put the car in reverse and then just gun it for a long time, and you could rewind the odometer and maybe sell the car for more. Can't do that anymore. Okay, so how are they related? Well, if a wheel does one full spin, okay, if a wheel does one full spin, then it moves forward by one circumference. Okay, I hope that makes sense. So if I have a wheel, and I guess I'll try and put something on the wheel so that we can see. Okay, so I have this wheel, and the wheel roll. So right now the piece of the sticky note is at the top. Okay, so if I roll the wheel so that please don't come off. Gosh darn it. Hang on, let me try this again. Okay, so I roll the wheel so that it does one full, gotta get this correct. So it does one full rotation. See, the tape is back up at the top. Then the amount that it moved forward is the entire circumference of the wheel. Okay? Oh, I thought of a really good way to demonstrate this. Give me a second. Okay. Got some toilet paper in the house. All right. We're going to do a little toilet paper demo here. All right. So, this is my toilet paper of science. So I'm going to draw a line right here. So hopefully you can see that. Let me do this. So here's a line. Okay. Like that. And I'm going to do one full roll of the toilet paper. Okay. So look at, the line is back up at the top. All right. And I can see how far the toilet paper went because of this. All right, so there we go. This is how far the toilet paper moved forward when I rolled it by once. Now let's see. I'm going to wrap this around the roll of toilet paper. And it fits. Look at it. It fits exactly. So if the toilet paper does one full rotation, it moved forward by one circumference. This is one circumference of toilet paper. I'm going to save this for later. Could come in handy. That was a really good demo. I'm pleased with myself. All right. So, if something is rolling, then your delta x is going to be equal to the circumference of the circle, which is 2 pi r. That's if you do one rotation. This is over one rotation. Okay? So now what I'm going to do is I'm going to divide both sides by the time it takes to do one rotation. Okay? Now, displacement over time, that's velocity. Okay? And then 2 pi over the period, 2 pi is one full rotation, so that's like delta theta. Okay? So we have change in angle over change in time, which is angular velocity. All right? So the linear speed and the angular speed are related when you are rolling without slipping. And this is when rolling without slipping. Okay? And this is an important part, without slipping. Can anyone think of a situation if you are in a car where the wheel is rolling while slipping? Type it into the chat if you know. Okay? All right. So what I can do is I can take this. Let me just talk a little bit intuitively about what this says. This basically says that the faster the wheel is spinning, the faster you're going to be going. And I think that's obvious. If you're on the freeway, the wheel is spinning faster than if you are driving through a parking lot. Okay? The faster the wheel spins, excellent. Yeah. So, but there's so I see some responses in the chat. So what do you say when it's rolling and it's slipping? There's like a specific term that I'm looking for. Yeah, icy roads would cause you to do this. I guess the word I was looking for is peeling out or skidding or drifting. So if you're in a car and you peel out, then the wheel is spinning, but the rate of rotation of the wheel is not related to how fast the car is moving, right? When you peel out, the wheel is spinning really fast, but the car isn't translating very fast. Okay, that's what peeling out is. And if you skid to a stop, the wheel stops spinning. Okay? The wheel stops spinning, but the car is still translating. Okay, so you get this. So when you're peeling out or when you're skidding, you break this relationship between the two. So this relationship is only true when you're rolling without slipping. Okay. So anyways, we can take this and we can rearrange it. So we can write omega equals V over R. Okay? And then I'm going to take this and I'm going to plug it into that equation. Okay? So your kinetic energy, all right, while rolling is going to be equal to 1/2 mv squared plus 1/2 I times V over R, quantity squared. Okay? And then I'm going to take this second term and I'm going to multiply it by m and I'm going to divide it by m. All right? And so I'm not going to show the math, but you can do some math on this. I guess I'll show the math. Why not? So let's talk about this second term. All right? So I can write it as 1/2 mv squared times I over mr squared. So that's just that second term. So see how I have v squared over r squared, v squared over r squared, and I have m over m, m over m. All right? So now, going to the other page, your total kinetic energy while rolling is going to be equal to 1/2 mv squared times the quantity 1 plus inertia over mr squared. Okay? So this 1, this is the contribution from translational. This I over mr squared is the contribution from rotational. So while you are rolling, you have both translational and rotational kinetic energy in that wheel. Okay? So there's a little bit extra. It's 1 plus something. So this is the extra kinetic energy due to the rotation. Okay? And so we can use this in energy problems. So let's do an example. Let's suppose that you have a solid disk. Okay, rolls without slipping down a hill that is, let's say, 40 meters high. It's a big hill. All right. So we have, here's the hill. The hill is 40 meters high. And you have this disc, and it's going to roll without slipping down the hill. And it's going to get to the bottom. And once it gets to the bottom, we want to know how fast is it translating. All right. Okay. And this is a solid disk, so I will fill that in. It starts at rest. So, if it starts at rest, this is just a regular conservation of energy problem. So the energy at the top of the hill is equal to the energy at the bottom of the hill. Okay? At the top of the hill, we have gravitational potential energy. So we have mg(y). And at the bottom of the hill, we have the rolling kinetic energy of the solid disk. Okay? So that's going to be 1/2 mv squared times the quantity 1 plus I over mr squared. All right. First thing I notice is that the masses cancel out. This mass cancels out with that mass. Okay. Gy equals 1/2 v squared times the quantity 1 plus I over mr squared. So now we're going to do a little tricky trick. So whenever you do these problems, whatever is rolling, I will always give you the inertia of that thing. Okay? So the inertia of a solid disk is 1/2 mr squared. Okay? That's the inertia of a solid disk. So that comes from calculus. So this isn't a calculus-based class. So that means I would just give you that result. Okay? So I would just say a solid disk is rolling. Solid disks have inertia 1/2 mr squared. So if I take this and I divide both sides by mr squared, okay, I get I over mr squared is equal to 1/2. Okay, so it kind of looks like our answer is going to depend on mass because you have m right here, but it actually won't depend on mass because inertia also depends on mass in such a way that the masses cancel out right here. Okay, so giving the mass of the solid disk was not relevant to how fast it's going at the bottom. Okay, just like with roller coaster problems, it didn't matter what the mass of the roller coaster cart was. So that means that 1 plus I over mr squared is going to be 1 plus 1/2, which is 3/2. Okay, so going to the next line here, I have gy equals 1/2 v squared times 3/2. So that says gy equals 3v squared over 4, which says that v equals square. So when I multiply that over, I get 4/3. 4/3 gy square root. All right. So that's going to be square root of 4/3. Gravity is 10, and the height is 40 meters. So 4/3 times 10 times 40 square root. And I get that it's going to be going at 23 meters per second at the bottom of the hill. Okay. So, important point I want to make. And this will be the last part of this lesson. Suppose you had something sliding down a hill. So something is sliding like a hockey puck or a skier sliding down a hill. So sliding down a frictionless hill. Okay, versus something that is rolling down the same hill without slipping. Okay, and so the question is, which one is going to be faster? okay? And it turns out, so for example, if you had a skier versus a ball that's rolling down a mountain, okay? Skier versus a ball that's rolling down a mountain. Same slope. Which one is going to go faster? And it turns out that the skier will go faster. This is assuming that the skier isn't doing any turns or anything. The skier is just going like that. Okay? Why is that? Well, if you think about it, in order to roll, you have to have friction. Okay? Rolling requires friction. Because if you think about it, if something is rolling, well, what would start it? What would start its turn? Okay, what makes it start spinning? Friction is the thing that makes the wheel start to turn. Okay. So, and that friction means that there's an opposing force to the rolling, which makes it go slower. Okay. If you're sliding down a frictionless hill, there is no friction. Another way to think about it is if you're sliding, then you have gravitational potential energy becomes translational kinetic energy and just translational kinetic energy. If you're rolling, you have gravitational potential energy becomes translational kinetic energy and rotational kinetic energy. Okay, so your potential energy is being split and going into two different places. Here, it's only, the potential energy is only going to one place. So you're going to have less translational kinetic energy if you're rolling, because some of that potential energy is going into rotational kinetic energy. All right. So this one is going to be faster. All right. So that's my lesson for today, and I will see you in the Zoom room. Okay?